Thank you very much, and thank you very much, Wes, for a very kind introduction. So clearly it's obvious who my employer is. During my career, I spent a lot of time working on JVMs. I was at Oracle, and before that at Sun in the Hotspot team for over 7 years. Then after a short stint at Adobe, I've been at Twitter in the Twitter VM team for just over 3 years now. And at Twitter, we of course evaluate technologies that we're going to use in the future. So currently we're on Java 8, but Java 9 is coming. So we started looking into it. So I'm going to share some of my experiences about Java 9. So as we know, Java 9 is almost upon us, right? So this was the initial prediction, and well, it's been pushed out a couple of times. So hopefully, in July of next year, we're going to have the first general availability release of Java 9 that we can all move to and start using, right? So what are the new features, the new interesting features that that will appear in Java 9? Well, the obvious one is Jigsaw, the new module system. I would like to take a moment now to say that I know everybody's complaining about the delays. However, this is a huge task, right? You have a very mature language. You try to retrofit it with a module system. This is a huge and complicated task. So give them a little bit of slack about the delays. I'm glad that they're trying to do it right rather than rushing and getting wrong, and then we'll have to live with warts for many, many, many years to come, right? So everybody's been talking about Jigsaw. Well, what else is there in Java 9? Well, Gil in the morning touched on a little bit, but well, there is a long list of features in Java 9 that nobody talks about because everybody's obsessed with Jigsaw. Right? So for this talk, I'm going to concentrate on a few of these. Okay? And in particular, I'm going to concentrate on 3 and on features that are related to performance tuning, profiling, etc. So the first one I'm going to touch upon and is going to affect a lot of folks is the unified JVM logging framework. And we all have GC logs, right? So hands up, who reads GC logs at work regularly? Okay, a few people. Who hates GC logs with a passion? All right, excellent. You have the idea. So for anybody who hasn't seen GC logs, I'm going to give a little bit of a kind of overview and why they're terrible and why the JVM, the new logging framework is going to help us a lot from 9. So here is an example of a GC log. If you just type java.h, it will show you, hey, you have this option verbose that you can say GC, and you enable verbose GC, and you get something like this. And every log record represents a garbage collection. You have some information about what caused the garbage collection. It's a location failure in this case. You have a heap information before and after and how long the GC lasted, right? So that's the verbose GC information, and nobody uses verbose GC if they're really serious about doing GC tuning because it has very, very minimal information, and most of the time it doesn't tell you, what went wrong during the GC, what happened, and what potentially causing the issue. So the minimum number of arguments command line arguments I would recommend that you enable, and again, we have to survive with Java 8 for the time being, at least until July, so this is not too late to actually start using these options, right? The minimum number of parameters are these. And if you enable them, I'm going to cover the first 5. The last one basically sends the GC log to a file. It's very, very helpful, so it doesn't mess up your output, right? And the output doesn't mess up the output of the GC log. So please, use that option. So I'm going to show you what the other 5 do. So the output from a single GC looks like this. And somebody looks at it for the first time, and it's like completely overwhelming, right? So I'm going to kind of go slowly through it and dissect it a little bit. So first, PrintGCDetails. The first thing that shows you is that there was a GC, the cause of the GC allocation failure. By the way, there was no failure, right, in the VM. What that means is basically the allocation could not be satisfied because the young generation was full, and it has to be collected before the allocation can be satisfied, right? But having failure in the log just freaks out everybody who hasn't seen this before. So don't use the word failure in a log when there's really no drama. Okay. Okay. So during the GC, the PrintGCDetails will also show you the different parts of the heap that were collected. In this case, there was a young collection, and that's what the par new shows. And the young collection took just under 38 milliseconds. And then only the young collection happened during this GC, so the whole collection was 38 milliseconds. The other thing that PrintGCDetails also shows is the CPU times. It shows user, system, and real time as measured during the GC. And this is really helpful. For example, if suddenly your GC times go up, but the user time doesn't go up, stays roughly the same, that means that maybe another process started running on the same machine, preempting the JVM, right? If you suddenly start seeing system time going up, maybe the JVM is paging. Right? And this will cause very, very long GCs. So from those, you can actually get like a better idea what happened and whether an external event started affecting particular GCs or is really the heap shape itself. So in orange, we have the output from PrintGC timestamps, which is in timestamp in seconds from when the VM started. And this is very helpful because you can tell how far apart the GCs are. In blue, we have the output from print heap at GC. And this is very, very helpful. It tells you for every space in the heap, in the young generation, the spaces within the young generation, either survivor, in the old generation, the meta space, it tells you what the occupancy was and how big the space was before and after the GC. And that's really helpful because you see what's growing in the GC, whether a particular, whether the old generation is growing fast or slow, or how full the survivors are, etc. This is very, very useful information. Then in magenta is the output from print reference GC. This tells us how long the GC spent processing references. References here are basically instances of classes that the subclass Java lang ref reference, right? Like weak references, phantom reference, etc. So again, sometimes maybe the application is using a lot of finalizers. Suddenly your GC times go up. Maybe they're caused they're caused by the final reference processing, which is related to finalizers being very high. Finally, print tenure distribution shows you how many, that's in green, shows you how many bytes per age cohort were copied within the young generation. And by an age cohort is like objects that have survived a certain number of collections in the young generation. So age 1 is objects that have survived 1 young collection, 2 objects that have survived 2 young collections, etc. And this is very helpful because it tells you the lifetime or expected lifetime of your short-lived object. So if that changes, maybe something's going on in the application, or maybe that could be reflected on the GC times go up. So all this information is really helpful. This is what we enable at Twitter, where we have an elaborate monitoring infrastructure that my colleague Megan talked about yesterday. But when we need to drill down on what's going on for a particular VM, we do look at GC logs. And all this information is really helpful. However, it looks like a freaking mess, right? And apart from all the nice colors that I used, right? So at this point, I will, allow me to give you a quick overview about why the GC logs are terrible, right? So where do I start? So first, lines are split. So this was to be one line. But because we enabled print reference GC and print tenure distribution, the output basically was generated between the first part of the line and the second. This is why the line is split. And I don't know whether you can see that from there. I hope the curtain is not at the front. There is an orphan colon at the bottom left. Why is it doing there? Well, the output is supposed to be square bracket par new colon, and then tell you something about the young generation. But again, that's split because of the extra lines in between. There's a distinct lack of white space, especially before timestamps. There is a lot of oops, I'm sorry. I got too excited about this. So there is a lot of unnecessary info. What the hell is this? These are the address ranges of the different parts of the heap. Why is it helpful, and why is it filling up my log? There is duplicate information. So the occupancy before and after the GC is replicated both at print heap GC and with PrintGCDetails, right? So all those complaints now, there are the mild ones. Now let's go to the uglier ones. So this is a full GC. So let's kind of drill down on the important parts. Well, instead of GC that we're saying before, now it says full GC. And remember, then it tells us which part of which space in the heap was collected. In this case, instead of par new, it says CMS, right? Because CMS is the CMS old generation, and the old generation was collected now. So we have square bracket CMS colon, and then it tells you that the old generation was collected, and then it took like 1.4 seconds, right? Now let's look at this GC, which says GC says par new, but it took 2 seconds. Why this young GC was so slow? Well, actually, it was a full GC in disguise. So with CMS, even if it doesn't say full GC in the log, there might have been a full GC. And the way you have to recognize it, of course, is by looking for the string square bracket CMS colon, because that tells you that part of that, that collection, the old generation was collected. But I actually lied, because the string square bracket CMS colon doesn't appear because, again, it's split by some extra output in the log. So it's a complete mess, right? It gets even worse, believe it or not. This is a similar GC to the one I showed you previously, but if it's not obvious now, the line is actually split because some other output from a different thread, so in this case the concurrent marking thread, is generating some GC logging output and was emitted halfway through the output of the other GC. So now you have randomly interleaved output from like 2 different threads. And this is a mild case that you can maybe be able to parse, but some cases so like messed up that it's just impossible to actually make any heads or tail of it. So why GC logs suck? I've been dealing with this for years. So formatting is inconsistent. I didn't touch on this, but different formatting for each GC. So you know, not only you have to write the code to parse one, let's say the CMS log, you have to write the code again like 2 other times to parse, if you want par old and G1. There's missing information, output is split, and also concurrent output causes like random interleaving. And because of that too, basically, they cannot be parsed reliably. I mean, everybody has some sort of, usually Python script that can parse them, and it doesn't work all the time, or it misses information. It's terrible. I mean, it's 2016. I mean, come on, really? OK, so thank you very much for listening. But still, going back to this, this is really, really, really interesting information in the log that we learn a lot from it. So let's see how we'll be able to get the same information in JDK 9 with a new JVM unified logging. So the first thing to point out is that all those parameters that I mentioned, they are gone in JDK 9, right? They're not like deprecated, they're just gone. So let's all take a moment to commemorate their demise. And yeah, I know, it's supposed to be a joke. Yes, I know it's blank. and thank them for the service, OK? You spoiled it. Now, our new favorite argument in JDK 9, OK, take note, don't do that joke again. So our new favorite argument in JDK 9 is going to be xlog, OK? And there is only one command line argument xlog, and then you pass lots of options that you control the log in different ways. So I'm just going to kind of build up on that over the next few slides. So the simplest version is basically xlog colon and a tag. In this case, GC, log colon GC. It will enable log records that are tagged with a tag GC. Okay? And there are many tags. So a tag kind of corresponds to maybe like a JVM module. Like we'll have GC, we'll have class loading, unloading with class, exceptions, OS, etc. But I'm concentrating on GC because, hey, I'm a GC guy, right? And I'll be talking about GC logs. I hope it's OK. You can also give a logging level for a particular tag. So you say tag equals and the level. So in this case, xlog GC equals debug. So it will enable debug level, logging level for the GC tag. And the levels are apparently what most people expect. Error warning, info debug trace. If you don't give a level, it defaults to info. All right? So let's look at the output from a VM that I enabled xlog GC, which is equivalent to GC equals info, right? So this is a log record. It looks very familiar, right, compared to what we've seen earlier. And the second part kind of looks like verbose GC. The output I showed earlier is very, very similar. But the first part, there's some new parts in the first part. The first thing to point out is like the first part of the record is a timestamp. Again, it's in seconds since the start of the VM, right? Very similar to what we saw before. Something is going to catch a lot of people, though, is that this timestamp corresponds to the time the log record was generated, not the start of the GC. So if you want to find the start of the GC, you have to subtract, just from this, you have to subtract the time of the GC from that timestamp, OK? And it's different compared to like verbose GC. So keep that in mind. The other part of the output contains the level, in this case info, right? And then the tag that generated the log record, in this case GC. Finally, and remember the logging framework is not only for GC, but all the GC records have a GC ID. So this says that this GC was the 634th GC in the, in the log. And this is really helpful because you can have several log records that basically belong to the same GC, and that's a very easy way to combine them. You don't have to deal with like nesting and all that nonsense. So this is actually way nicer. So the tags are hierarchical. So we saw GC, you can actually add several tags that make sense, separated with pluses. So here we have xlog GC plus heap, and that will enable heap output, GC heap output, okay? And then if you want to enable all kind of sub tags, if you want of a particular tag, you can use star. So GC star will enable all the GC plus blah tags. So it's kind of convenient. And tag, not all tags combinations make sense. So I have some examples here. Heap ref and CPU make sense for GC, as we'll see a little bit later. But load and unload make sense for class. For class records, like enables class loading and class unloading log records. So apart from deciding which tags you're going to enable and at which level, you can also decide where to send the output. So after the tag and level output, the tag and level options, you can add the output option, which is colon, and then it's either standard output, standard error, or file equals in a file name. And you can omit the file equals if you want to. The default is standard output, as you'd expect. And the file name can actually include some special strings like it is the case for JDK 8, like %p, which will be replaced by the PID of the process, %t, which will be replaced by the time the JVM started, etc. These are really helpful if you're storing lots of logs on the same directory. They don't keep overwriting each other. You can kind of separate them. You can also control what decorators to enable. So after the output option, you say again colon, and then a series of decorators separated by comma. And different will enable, different decorators will show different things. Like time, it will show you a kind of a timestamp, kind of that shows date and hour and time and all that stuff. It's similar to PrintGCDetails stamps in JDK 8. Uptime is what we saw earlier. You can add the PID of the process as decorator, etc. So the default is uptime, level, and tags. So let's look at an example output. This is GC, and then we enable with the decorators time and PID. So instead of what we're seeing before, now you see that time generates this very elaborate date stamp, right? And then the second column is the PID. Why is this helpful? Maybe you end up sending the output from different VMs to the same place. So again, so you can reliably separate it. Something to point out, though, notice that the two colons in the option. So it's log GC colon time comma PID. Why is that? Because the syntax is that you pass the tag information, and then you pass the output information, colon the output, and then colon the decorators. So if I had only colon time comma PID, I had only one colon, that would be interpreted as a file name. So it will actually create a file name called time to comma PID, and it will send the log to that file, right? I really hate this. I find this really frustrating, but that's okay. So I've showed you enough on how to enable different things in the new logging framework. So how can we get output similar to what I showed you earlier in JDK 9? So this is the incantation. This is one line. Something I didn't mention earlier is that you can enable different tags at different levels, and you separate them by comma, right? So we have now GC star, so all the tags, the GC tags at info level, because that's the default, comma GC plus ref at debug level, and then GC age at trace level. Then we send the file to send the log to a particular file name, and we only enable the decorators tags and uptime. I don't think the level actually, showing what the level that generated a log record, I don't think is very helpful in the log. It just makes the log larger. And these are a kind of a one-to-one correspondence. These are roughly equivalent to the parameter I showed you earlier, roughly. So let's look at what the log looks like now. So this is from one GC with those arguments. So we have a log record at the start that says that's the start of the GC, a log record at the end that says the end of the GC and how long it took. We have the CPU times that I showed you earlier is very similar to what we're seeing with PrintGCDetails. Then again, with the GC start tags, we also get some heap information in blue. Again, the nice colors showing correspond to the colors I showed earlier, right? And using the uptime decorator, you now get those timestamps. And if you get the timestamp that was generated at the start of the GC, that's the actual timestamp that you want. Don't read the timestamp at the end of the GC, because remember, that's not the start of the GC. It's like when the log record was generated, as I said earlier. With GCref at debug level, we enable the referencing processing information, again in magenta. And finally, in green is the tenure distribution, and that's enabled with GC age at the trace level. Okay, so this is very similar information to what I showed earlier, and it's actually a lot more concise, which is really nice. So your log doesn't grow like a lot. However, there's something missing, and is that the much more detail about the heap shape. So here you have like a generating information about this was the occupancy of the young generation before and after, but I really want to know how full the survivors were, how full the Edens was, etc. That's really, really helpful information when we track things, issues down. Can you do that in iron? Yes, you can. Yes, we can. That's kind of appropriate for an election day. Man, everybody's asleep today. Okay, so, and you just enable the GC heap tag at debug level, and that's basically exactly the same output as with print heap GC that I showed you earlier. In fact, this is it. With all the extra useless information we don't need, but you have the exact heap information that is really helpful. Okay, this will triple your log size, I think, but it's really helpful. So if you can handle the extra size, it's really worth it. Okay, just a couple of quick things. You can enable log rotation. This is done with extra parameters in JDK 8. Here, you just add yet another set of options to the xlog command line argument. So file count 4, file size 16 megs. So the log will rotate up to 4 files, and each file is going to be up to 16 megs. And the cool thing is that you can actually enable different logs. So let's say we want to enable some basic logging like GC at the GC tag at the very basic level and send to standard output. So we're looking at the console to see what's going on, right? But then we want to enable more logging that goes to a file. You can pass different parameters. In this case, we'll just send much more information to the log file. So that's really cool. That's something you can do right now, and that's actually something very, very cool. I'm mainly concentrated on GC tags, but there are of course other useful things that you can, other useful tags that you can enable. Class loading and unloading is an obvious one, just to see where classes are being, they're coming from. Exceptions, so you can actually get log record for every time an exception is thrown, even if it's caught, of course. So if suddenly you think that, I don't know, your application is throwing lots of exceptions, so there is some performance issue, you can track it with that, etc. So in summary, this is a huge improvement, right? We have more control over the output. You can enable multiple logs. There is no interleaving and split lines anymore. Every log record is guaranteed to be on one line. There's no screwing around by different threads, et cetera. And it can be much more reliably parsed. So I'm definitely looking forward to not having to deal with the current GC logs and kind of dealing with this, which is going to be great. So hopefully you're going to find that helpful as well. Okay. All right. So moving on to the next topic, which I think is kind of cool. I don't know whether anybody's been keeping up with this. So it's compact strings. So I'll give a little bit of kind of how the string class evolved in Java, starting with like the beginning of time, the first Java release, up to JDK, up to Java 6. So until Java 6, string class had 4 fields. It had the value field, which was a character array that was pointing to the array that contained the payload of the string. It had an offset and a count, which defines basically the subset of the array that actually contains the payload that this string corresponds to, right? So if you want to do substring, you didn't have to replicate the character array. You could just create another string with different offset and count, get a different view essentially on the same character array. And finally, a hash field. So if you want to hash the string, you only calculate the hash once, because sometimes it could be time consuming, and then you store it and then you keep reusing it. Okay. So from JDK 7, they removed actually the offset and the count fields. So now you only have the hash and then the value field, which points to the character array. So now the character array basically always contains all the characters that belong, that string represents. And if you substring, then you might get like a new character array. There is a huge amount of performance trade-offs and other footprint trade-offs between the two different schemes. So, and I won't go into them right now. You can ask me later, but this seems to work pretty well in most cases. Okay. So now let's see how big in bytes a string of a given length is. So at least in hotspot, so we have 24 bytes for the string object. So it's the header of the string instance plus the payload. Then 16 bytes for the array header. And then 2 times the length of the string because characters in Java are Unicode, right? So there are 2 bytes each. So let's just pick an example at random. So let's say we want to calculate the size of a 140 character string. So it's basically 320. Yeah, only Wes got the joke. Everybody's like looking really serious. OK, so how can we improve on this further? So the observation is that if for example, strings are tweets, and I tweet in English, right, and you're generally using only the Latin character set, and you don't use Unicode, half of your character array is basically going to be zeros, because the characters can actually be encoded in 1 byte, and then the rest is not really going to be used, if you don't take advantage of the full Unicode. So it would be really nice to be able to, if that's the case, it would be really nice to be able to represent to have a different representation for the character array that is more compact. Okay, and this is exactly what the string class in JDK 9 does. So notice that we still have the value field, but now it's a byte array, it's not a character array. Okay, and we'll have a new field which is called the coder. The coder is either Latin or Unicode, and I believe it's 0 and 1. They're actually the actual values. And the coder tells you how the string is encoded. So if it's Latin, then the byte array has 1 byte per character. And if it's Unicode, the byte array has 2 bytes per character. Okay? And let's do the calculation again to see how much space this takes up. Now, again, the calculation is that, OK, so we have 24 bytes for the string object size. And you should be going, hang on, you added a new field. How can it still be 24 bytes? It was 24 bytes before when you didn't have the coder field. So it turns out that the VM aligns objects to 8 bytes. And there were like 4 bytes to spare from before, so that was lucky. So you add a field, and the object size doesn't increase. That's very nice. And yeah, if you use only the Latin character set, you don't have to multiply the length by 2. And now the string size of a string with 140 characters, it goes from 320 to 180, which is a huge improvement. So some numbers published by Oracle. So for typical applications, in double quotes, whatever that means, that mostly use Latin character set and don't use Unicode heavily, they observe a 5 to 15% memory footprint reduction, which is very nice. Your mileage might vary depending on how heavily you use strings. And they also observe 3.7% throughput improvement. And this is because of 2 reasons. First, the GCs are faster and less frequent. They're less frequent because now the strings are smaller, so it takes longer to fill out the young gen, right? And they're faster because they copy less, because now you don't have to copy 16 bytes per character. And also, the main reason why the throughput improvement, I believe, is because of better cache utilization. Now you can fit much more into cache line, much more characters into a cache line than before, so you decrease the number of cache misses. Folks might remember that anybody remembers this? In JDK 6 updates, there was an option, use compressed strings, that did something very similar. Okay, anybody remembers it? Yeah, a few people? OK. Oh, yes, Gil. Hi. So this is similar, but it's done kind of properly in double quotes. So the compact strings are actually a much bigger project. So it is on by default, because there doesn't seem to be a huge, or actually there's very little overhead, even if you use a lot of Unicodes. You just you don't have the footprint reduction, but there's not much overhead with that. It is more complete, and is done in a way that they changed a lot of other classes that kind of relied on the fact that they changed a lot of hardware, like string builder, that knows about the encoding, so you can actually pass the right thing rather than having to kind of encode and decode byte arrays to character array and back. Whereas use compressed strings, it was much more limited. It only changed the string class, and in order for anybody else to interface with the string class, the byte array had to basically be translated to the character array. So it's a much better approach. It has better performance improvements, and is much more maintainable. I believe one of the reasons they dropped it from 7, they dropped the use compressed strings option from 7. It was like it was kind of hard to maintain. Okay, so this is a very nice improvement in Java 9. Again, you kind of get it for free by just using strings. The string API doesn't change. It's basically all the changes are kind of under the covers. So the third topic I will talk about, which I personally think is really cool, is the new stack walking API. So first, why do you want to walk the stack from Java? So there are a few reasons why you want to do that. The most obvious one is logging. So you have some rare and maybe expensive event that happens. Maybe you want to take a stack trace and log it along with the event to maybe work out what caused it, what was going on, etc. Other reasons include, well, you have a library, you want to know who's calling to the library. You have to walk the stack, ignore all the other frames that belong to methods in your library, and just reach the one outside your library, and that's your caller. Another reason is to find the first privilege frame. So you need to do some access control on a particular operation. You go down the stack, find the first privilege frame, and know what kind of privileges it has in order to know whether it can do that operation or not. So in JDK 8 and earlier, the only way to get a stack trace was to call the getStackTrace method on thread. So that returns a big array of stack trace elements, one stack trace element per stack frame in the stack, and depending on how how deep your stack is, then that array could be quite large. And then you can just use it. In this case, I just iterate over the elements and just print the method name of each stack frame. Corresponds to each stack frame. So the disadvantage of this is that the cost is proportional to the stack depth. So the deeper your stack, so let's say you're, I don't know, 600, 700 methods deep, then it could take a reasonable amount of time to actually construct all those stack trace elements and add them to the array. And also the footprint is also proportional as well. And as I was showing earlier during the examples, you don't always need the info on all stack frames. You might need the info on the top 5 or the top 10 or something, and it's kind of a waste to get all this information and just throw it away. So in JDK 9, the new stack walking API improves on this by quite a lot. But I will take a couple of minutes first to describe why doing stack walking in a more flexible way is actually a very tricky thing to do. I don't know if it's obvious or not. It was not obvious to me initially. So this is a running Java thread. There are some stack frames on the stack. The stack grows up the way the magenta boxes correspond. Each corresponds to one stack frame, right? And that's, at this point, the thread says, I want to walk the stack. Right? And of course, you call some method which of course has to push like another stack frame on the stack, right? And let's say we want to do the iteration with, say, a stream. Okay? So we create, it creates a stream object. That orange blob is supposed to be a string object in the heap, right? That's pointed to by the top stack frame, right? And the stream object knows how to go to the first stack frame that is below the one that created it. Right? It has its address, say, that it can go and look at the information, and then from there it can go to the previous one, etc. Right? Straightforward. Now, if we're not careful, remember this is just the stream object is just an object in Java. So if we're not careful, what we can do is we can return from a few methods. Right? We now go down the stack and pass the stream object up, or actually down the stack in this case, right? And then we can just call some new methods now, and then pass that stream object as an argument. And now the top level frame has a pointer to the stream object. And if we try to do an iteration, we're going to crash and burn, because the stack just changed under our feet. Right? By virtue of just returning from a message and calling new methods, you just basically messed up the stack. So, and there's no reasonable way, there's reasonable performance trade-off to actually keep up. Keep what's in the stream and what's happening to the stack to keep them in sync. It's just it's way too expensive. It would be impossible. So the way to fix this is we have to ensure that when you're doing the iteration, you should never basically go below that top frame. So all the stack frames that the stream knows how to iterate over, they remain basically intact. So it can iterate over them safely. And this is exactly what the new stack walking API does. So there's a new class, stack walking in Java lang. And instead of just returning a stream, which is the obvious thing to do, right? And I just explained it's a very unsafe thing to do. Now it has a walk function, a walk method that takes a function that takes a stream of stack frames. I will tell you a little bit later what a stack frame is, and returns a result. And that result is returned further by the walk function. So you're into lambda heaven here when you start doing the stack walking. So here's an example was similar to what I showed earlier. You just you call walk, and you take the stream, and then you map the frame to the method name, and then you just print the method names. Right? This is a similar example to what I showed earlier. So why is this safe? There are a couple of reasons why. Actually, the main reason is that the stream cannot be used outside the walk method. It is possible if you're like really naughty, you pass a lambda that stores the stream to a static field or creates a new thread and passes it to the other thread, so you can actually even run, the new thread can run concurrently with the walk method, right? I've tried all this just to see what's going to happen. And it turns out the stream cannot be used outside walk for a couple of reasons. First, it is closed before walk returns, so if the same thread tries to access the stream, we'll get an exception. And also, it cannot be accessed by any other thread. So when the stream is created, it has a pointer to the thread that created it. So if another thread tries to access it, it would just get an exception as well. So the stream is only really usable within the walk method. And this is what makes this iteration safe. So I have just a few examples. And as I said, this is just more like an exercise on how to do something with lambdas. So here we want to get like a series of interesting frames, whatever an interesting, in double quotes, right? Whatever an interesting frame is. So it's very straightforward. We take the stream, we like filter it based on a method called is interesting, and then we collect into a list. This will go through the entire stack, but will only create a list of the frames that are interesting. If we wanted to limit it, it's easy. You just add a limit, 32, and this will only look up to 32 frames, and it will not go further. So this is a very nice way to kind of bound the cost of this operation, both in terms of memory footprint and also in terms of time, how long it will take to finish. And if you want to pick a particular frame, again, you can filter it based on something and then return find first, and then you get the result, or not, because it returns an optional, because there might not be a result, right? So the stack frame interface that I showed you earlier is inner interface of Stackwalker, with apologies for the slightly dodgy syntax there. So it's an inner interface of the Stackwalker class. It has methods similar to what the stackTraceElement class has. So you can get the class name, you can get the method name, blah, 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 blah. But on top of this, you can get the declaring class, the class whose method, the method that of the frame belongs to. And it's interesting because if you only have the class name, you cannot always get the class. Right? Why? Because of class loaders. You can have the same class with the same name loaded multiple times by different loaders, so you don't know which one it is. But with this, you can. And there's also a convenience method that translates a stack frame to a stack trace element. If you already have code that operates over stack trace elements, you can just use that. All right. So just to summarize, the new stack walking API is actually very flexible and powerful. It has way better performance characteristics compared to what was there before. And I believe there are several parts of the JDK have already been updated to use that instead of whatever scheme they were using before. And it might kind of allow stack walking to be done in certain situations that before it was too expensive. Like, for example, you have some logging system, and you say, well, I cannot afford, we log reasonably frequently. I cannot afford get like a full stack trace because it's too expensive, but I can afford, look at the top 5 frames and just log that, just in case it's helpful. Before you're going to do that, maybe now you can do that. All right, so I covered the 3 main topics, and we'll have a bonus topic that I will cover last that I think is very cool. So using the immortal words of Morpheus. So what if I told you you can write a just-in-time compiler in Java? And this is exactly what you can do with the new JVM CI, the Java JVM compiler interface. And by compiler, we're talking about the JIT that translates bytecodes into machine code while the VM is running, not Java-C, right? This is very cool. Everybody's like looking perplexed, or have you seen this before? Okay, people are looking perplexed, all right. So I will give a little bit of an overview how kind of the JIT works in Java and how it interacts with the rest of the VM. So when a method is executed in hotspot, it can be executed at 3 different levels. So first it can be interpreted, then compiled by, if it's hot enough, whatever that means, it's compiled by the client compiler, C1. And if it's like still remains hot, it will be compiled by the server compilers, C2. And all that stuff, if you enable tier compilation, that will enable both compilers to work in the same VM. And what's the trade-off between the 2 different compilers? the client compiler is a fast compiler, but generates so-and-so code. The server compiler is a much slower compiler, but generates much better code. Okay? So you want to compile with the client compiler maybe to kind of get improved startup a little bit, but ultimately you want to compile with the server compiler to have great throughput in the long run. So I'll cover a little bit the interaction between JVM and the JIT compiler. So the JVM has a code cache, and the code cache contains all the methods that have been compiled by the JIT, and that's how they're executed. For every method, it has a set of dependencies. So when the JIT compiles a particular method, it makes a set of assumptions. Like, for example, it can assume that, hey, the only class that has been loaded that implements the interface map is hash map. So every time I see an instance of type map, I can actually safely assume that it's a hash map, because it has to be. There's no other, there's no other class that it can be. So it can maybe generate better code, as, making that assumption, but it has to record that assumption somewhere, because maybe 5 minutes later, tree map is loaded, and it validates that assumption. And in that case, the VM has to go through the dependencies and invalidate parts, several compiled methods that have an assumption that doesn't hold anymore. On top of this, of course, the JVM has a lot of metadata, like class information, class bytecodes, method signature, field signature, blah, 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 all that stuff, what's in the class file, basically. And also maintains lots of profiling information. Which methods are hot, which part of methods tend to be executed more, so which paths through a particular method tends to be hotter than others, etc. So when the VM notices that a particular method is hot, it tells the JIT, can you please compile this? And the way it does that, it usually just adds that adds that to a queue that the compiler basically looks every time it finishes a compilation. So the JIT starts compiling the method, and it has to request a lot of information from the VM while it's compiling the method. The information includes, give me the bytecodes. Give me the signature of that method that is being called. Give me the bytecodes of that method. Maybe he wants to inline it. Signature of fields, layout of objects, because the VM ultimately decides what the object layout is going to be, etc. Finally, when the code is, when the JIT finishes and finishes the compilation, it puts the generated code in the code cache, right? You see the new items that appeared there, right? And then also remember that it has to also add the set of dependencies that that code depends on. It's basically the assumptions that the JIT made while it was compiling that method, just in case they're going to be invalidated later. So how does this work with JVM-CI? So when you enable JVM-CI, basically the JVM-CI compiler, which is written in Java and implements interface JVM-CI compiler, it replaces the server compiler. Okay? And JVM-CI, the interface, basically defines that interaction between the compiler written in Java and the VM, and does so in Java. Okay? And what I tried to say earlier is that a lot of the interaction is not like give me, compile this method, okay, here's the result. The result is usually like, I think, a byte array, right? It returns the machine code in a byte array. So a lot of the complexity of JVM-CI is just the interaction between the compiler and the JVM when the compiler needs to get metadata information from the JVM, profiling information from the JVM. Here is the set of dependencies that you have to add to that method, etc. So this is a lot of, what the time, so this is a lot of where the complexity for JVM-CI is. So why you want to do that? Why you want to write a JIT in Java? Well, it's easier to write and maintain, right? I assume, like most people here will assume that writing Java is easier to write and maintain than like C++. It is safer, so compilers have bugs, right? If C2 crashes, it takes down the VM. In this case, if the compiler has a bug, it will throw an exception, right? And it will be caught, and that compilation will be abandoned, but the VM stays, and then you can just call it again, right? And it is pluggable. And this is actually pretty cool. So imagine, and I'm kind of being a little bit optimistic here, but imagine like you're Charles Natter, right, who's been working on JRuby for a long time, right? And then he comes up with a really cool way to optimize JRuby bytecodes in the JIT. But if you wanted to release that, currently he has to release his own JVM, which is kind of not easy, and he has to basically release every time, release an update every time a new JVM, a new JDK update goes out. But maybe with this, you can just distribute the JIT along with JRuby, and then it would just, and the VM would just pick it up without having to, rebuild the VM, et cetera. And it's actually pretty cool, right? One thing to point out, though, is that, write once, run anywhere. Well, this doesn't hold here for a couple of reasons. And maybe everybody's going to be surprised that this is the case. But there are a couple of reasons. First, the JIT generates machine code, so it generates machine code for a particular architecture, right? So in order to make it usable for more architectures, then you have to basically have a JIT that with different backend, okay? And the second reason why it's not necessarily portable is that a particular VM has certain, it does things in a certain way, like the way allocation works is different in hotspot compared to J9. The way synchronization works is different in hotspot compared to J9. The JIT has to kind of generate code that deals with synchronization or allocation, et cetera, just to get best performance. So the JIT is, the JIT can be actually targeting a specific VM for a specific architecture. So it's not as portable as you expect, but it's still easier to write and maintain and all that stuff. So yes, there is a JIT written in Java. It's called Graal. It's a high-performance dynamic compiler done at Oracle Labs. Interacts with Hotspot through JVM-CI, and it's open source. And you can download it. You can download that JDK 9 early access. And then there is like a long set of command line arguments that you have to pass. There's an incantation, and then you actually up and running with a JIT in Java. And a couple of things if you use Graal. So who compiles the compiler? So the compiler is Java, right? First it's going to be interpreted. And then, currently only C1 will compile the compiler, because by the time the compiler gets really hot, you probably can compile a lot of things, so there's no point in optimizing it further. However, there is another JAP that was recently announced, the ahead-of-time compiler, that will be able to compile the JIT compiler ahead of time, so you don't have to compile it when the VM starts up. Right? And interesting enough, the ahead-of-time compiler is also Graal-based, so in this case, Graal will be compiling itself, which is kind of pretty cool. Something to note, though, is that there is some extra heap overhead and pressure if you're using Graal. Why? Because it's just a Java application, right? So it will create data structures in the heap, and it does have some state that it maintains between compilations. So there will be some extra overhead in the heap if you're running. So you have to take it into account when you size your heap. And just to summarize this, so this is my colleague, Chris. Before he joined us, he was actually in the compiler group in the Hotspot compiler group at Oracle, and he worked on this. And this is actually a real tweet. I usually kind of have joke tweets sometimes, but this is a real tweet. And he said, this is one of the most important things I've worked on in a while. So that's all I had. Thank you very much for coming. Thank you very much for coming. Even though the title of the talk did not have microservices, serverless, agile, and I don't know what else. So it was great to have you here, and I can take questions. Thank you very much.
Any questions? So in the beginning, you listed big list of the features.
Yeah.
So any other features that notable that you can tell like in 5 seconds?
Oh, I can't remember which ones to pick. So Gil went over a few of them earlier. Not sure. I tried to kind of keep two features that kind of had to be kind of performance and profiling related. So these were the ones that kind of I found interesting. Yeah.
So the unified JVM logging,
Yep.
is there another set of options after another colon where you can specify the format of those logs?
No. No. So yeah, that's a good question. So no. So yeah, apart from the decorators that anything after that is basically a string. So and it's generated as a string. So Hotspot does have a way to log in a structured format, which is JFR, and it's an Oracle product, and it's not an OpenJDK. So if you want to do that, you have to basically use an Oracle product to do that. Yeah. And anybody else? You can. I'll hang around here if you want to come and grab me
Tony will
afterwards.
be up here. If you're going to go to the Java open space, it will be in the Pacific BC downstairs.
Yep. Thank you.